In this series of examples, we're going to explore what happens here in a weld when we take two plates and we butt them up together and weld them across and then load it up. So the axial load on this system is the 100 kilonewtons. The plate is 80 millimeters wide, 10 millimeters thick, and the angle of inclination of the weld is at 20 degrees. All right, so the first step and the first thing we'll do is we're going to label an appropriate stress block for this situation. And notice how the way this weld line is drawn here, and that beta tells us that this dashed line on this perspective drawing is the vertical line over here, right? So beta is equal to 20 degrees. And being a uniaxial loaded situation here, then all we're looking for is the axial stress that we have to put this thing into pure tension from an axial standpoint, right? And so that sigma is just our P over A, and that would be our 100 kilonewtons divided by 80 millimeters and 10 millimeters. And of course, that's just 100 divided by 800, and that would be 0.125 kilonewtons per square millimeter, which is the same thing as 125 newtons per square millimeter, and newtons per square millimeter is a megapascal. So our tensile stress is 125 megapascal on those two planes. Now there's no shear stresses on those planes and no normal stress on the other plane, right? Just pure uniaxial tension. Right, so now let's construct more circle that's associated with this, and then we'll figure out where the point W might be. Right, so we've got tension to the right, compression to the left, clockwise shear stresses up, counterclockwise down below. And this point here, let's call it point A, will then have a 125 tension and 0 shear, and point on the other plane, point B, we'll call it. I know B and beta are a little confusing, but we got 0 and 0 on that one. So point B is right there at the origin. Point A is out here. We don't want to make it too big because we need to be able to draw it on here. So I'm going to choose a scale of a circle I know I can get on here. And well, there's our circle. There's point A, and that's out here at 125 megapascals. Right, the center of this thing is then at half of that. So 125 divided by 2 is 62.5, which will also be our radius here. But we want to go find this point on this weld, right? So the W that represents the weld here, if we look at its normal, then its normal is sticking out like that with the white ruler. And that's 20 degrees, just like beta itself is 20 degrees. Right? So from point A outward normal to the point W, that is the weld orientation, is 20 degrees in a clockwise fashion. So here's A, 20 degrees in real life becomes 40 degrees in more circle world. And we go in the same direction. There's your 40 degrees. And there is point W. Right? And then all we have to do is figure out what the normal stresses are that go along with that. So that would be right there, and the shear stress would be that vertical portion. Right? So the radius is 62.5. So this tau value then is going to be opposite. So that's going to be 62.5 times sine of 40 degrees. And that will be equal to, double check that, 62.5 times 40 sine equals 40.1 megapascals. And that's going in the counterclockwise fashion for, for that one. And then we need to find this other one. So that's our normal stress. That will be the average, 62.5, plus then 62.5 times cosine of 40 degrees to get out to that coordinate. Well, 62.5 times 40 cosine plus our 62.5, and that's 110.4 megapascals in tension. So that will be the stresses on the weld, and that's what they're asking us to do here. Use Mohr circle to determine the normal shear stress of the weld. We just did that. Draw and label a properly oriented stress block for these stresses. All right, so let's draw the stress block. Really easier to use a square template here, but we'll get pretty close. All right. The weld is on this side. This is the one we just found. How do I know that? Again, that goes back to, there was the physical weld. The normal to that weld was, of course, perpendicular to it. And so when I go this way, that means the solid is over here to the left. So that's how I know that we're talking about that one right there. And so there's your 110.4. These will all be in megapascals. And then counterclockwise on this same surface for the shear stress, that is 40.1. Now, knowing one tells me I know all the rest of them, right? Because that one has to be that way. The shear stresses have to pinch together. And I know the normal stress on the opposite plane. It's got to be 110.4 also. And the only thing I don't know yet are the normal stresses on that plane. So let's go look at what's going on here. Right, to go from W over to W prime on Mohr circle is 180 degrees. Right? Now, that's 90 degrees in real life, so that's to either one of these two planes. If I march in a way that goes from that W this way, right, so going around this way, it means I'm rotating the outward normal in a clockwise fashion, 180 degrees in Mohr circle, 90 degrees in real life. So that would mean going from then here over to this one would be this point. And so we get a clockwise, oh, well, that's what we've got here. And we got to go find that little value. And that's going to be 62.5 minus that. So 62.5 minus 62.5 times 40 cosine will leave us a small net of 14.6. That's still in the positive region. So that means that's still a tensile stress. And of course, they have to be the same. And you say, how do you know that from Mohr circle? Those are 180 degrees apart in real life, so 360 in Mohr circle, going all the way around, right? And you're like, if you're going around the circle, what do you mean degrees? Well, I'm rotating this radial line, right? So it's that angle that are showing up in here that matters. All those kinds of angles are what matter, right? And that's how you do those three example problems.